Welcome, everybody. So today I'm going to talk about something that I usually don't talk about, and it's portable accelerator programming with SYCL. So SYCL is a C++ based programming language, and you'll hear a little bit more about that. Usually, the software that I develop is written in CUDA and HIP to run on GPUs, but we are also working on a project with SYCL, and so that's what I'm going to talk about today. And so the agenda in principle looks like this. I'll just give a brief overview about, why we're using accelerators nowadays. Then I will give an overview of SYCL and oneAPI, a brief introduction to programming with SYCL, and finally I'll spend probably the last third to maybe even half of the talk to go over the porting of the AMBER molecular dynamics code that we've been doing in collaboration with Intel over the last few years to SYCL. And just to get started, I want to just briefly bring up the question about, what is an accelerator? And basically, it's a specialized hardware component to speed up some aspect of a computational workload. And there are many types of accelerators. So, you have your CPU in your laptop, but you have a graphics processing unit in your laptop. There's neural processing units or whatever AI accelerators that, people call them nowadays. But we have other accelerators as well, as something like programmable gate arrays, FPGAs, or now coming, and who knows, over the next few years, quantum processing units, QPUs, for instance. And so these different types of accelerators are useful and good for different types of applications and compute workloads. And if we step back a little bit and look at, the microprocessor trend over the last decades, it explains a little bit, why we have accelerators and why we're using accelerators so much also in scientific computing. And so you're probably familiar with Moore's law that says that the transistor count in integrated circuits doubles about every 2 years. And you can see this here on the plot on the right in yellow. That trend still holds, but there's something else that you see that has emerged since the mid 2000s about here is that because we can, Dennard scaling is basically came to a limit, so we cannot shrink the features, the integrated circuits on our chips anymore. The clock frequency basically has started to level off. Single thread performance still increases if you're looking at a CPU, but of course it's not an exponential growth anymore. And what happened instead is basically the performance increase that we have on a single chip nowadays is chips also becoming bigger, is the increase of CPU cores per processor. And the second thing is that we have hardware specialization, for instance, GPUs. And the impact on our software is that we cannot simply wait 2 years to double our code execution performance, but we must write parallel code. And there are different ways of doing this. And so one of the most famous accelerators that's not used only for graphics anymore, graphics processing units that have emerged over the last 20 years. And these plots are a little bit outdated, but they're still quite useful to look at. And on the left, we see the floating point performance of GPU. We have like AMD, back then was called ATI or AMD GPUs here in red, and Nvidia GPUs versus like CPUs. And on the right, we see the memory bandwidth, so how quickly we can move data from RAM to the processor and back. And so the development of the GPUs has been driven by a lot of money in the gaming industry, and nowadays it's basically the AI industry that is pushing everything. So Nvidia has become, I think it's the most valuable company in the world, at least according to the stock market valuations. And that has been fueled by AI, investments in AI. And the reason is basically that, GPUs are very good at matrix algebra, and Nvidia has early on realized that, well, this can make AI applications as well suited for deep learning workloads, basically. But the main thing that you can see is that we have a much higher floating point performance and a much higher memory bandwidth than CPUs typically. And it has to do with the fact that CPUs are much more general processors for much more general tasks. They have much more complex like branch prediction units and so on. And so you cannot use, you have to devote some silicon for that. And GPUs don't do that, so they are optimized basically for compute and throughput and memory bandwidth. And with this are much more powerful. And if we look at computers like SDSC Expanse that we have at SDSC, it's our main NSF supercomputer for national research that we have at SDSC. And we look at the architecture. So one thing you see in here, there are GPU nodes. So even Expanse has both CPU and GPU nodes. It's an older system, 5 years, but it's still very useful. It's always loaded. People are using it a lot. And if we look at the node architecture, if you've been to this webinar series, you've heard webinars about that before. We have other webinars at SDSC that talk about Expanse in particular, also on how to use Expanse. So I won't spend much time on this, but each of the compute nodes that has GPUs has 4 of those GPUs. So we have a lot of computational power in terms of GPUs on that each of these GPU nodes. Not talking much about this, but if you look further in the current HPC environment for scientific computing, so this is SDSC Expanse that we have at SDSC, where we have AMD and Intel CPUs in the system and Nvidia GPUs. We also have a specialized computer that has only for AI supercomputing that has actually processors, some of these AI processors from Intel, so Intel Habana AI processors. And then we have a new testbed system that has AMD APUs. And APUs are combined CPU and GPU on a single chip. I'm also not going to talk much about it, but also the exascale computers, bigger systems that you see, the OE exascale supercomputers, they're also based on these accelerated processing units that combine a CPU and a GPU on a single chip, or CPU and GPU based, either Intel CPUs and GPUs or AMD CPUs and GPUs. And these are highly parallel systems. And all of them basically have commodity processors and GPU accelerators or special AI processors. And over 98% of the performance comes from GPUs. So if you want to make use of any of these computers, your software has to be able to make use of the GPUs. Otherwise, you're wasting a lot of resources or you cannot use the resources efficiently. And so the question then becomes, how do we program the GPUs? And traditionally, probably the earliest one is Nvidia that came out with CUDA for Nvidia GPUs. And it's the de facto standard for high performance code. They have very robust ecosystem, but it has the downside, of course, that it works only on Nvidia GPUs. We have HIP that's similar to CUDA. It works with Nvidia via CUDA backend and AMD via the ROCm backend. And so that is an open source C++ runtime API and kernel language that was developed by AMD. So if you program for AMD GPUs, you're using HIP. Now, HIP looks very similar to CUDA. And if you do it right, we're doing this in some of our codes that we're developing, like Amber and the quick quantum chemistry code, about 90% of the code path is identical between CUDA and HIP. So in that sense, you already have kind of like portable code because at least you can move between NVIDIA and AMD GPUs without having to do much programming. So then there are special code paths that use features that are, for instance, implemented only on NVIDIA GPUs, but not on AMD GPUs. And for those, of course, you have to use different, yeah, you have to program them differently. Then OpenCL has been around for a long time as well. It's an industry standard that works for NVIDIA, AMD, and Intel GPUs and also other devices. It's very often used for embedded processors. And it's typically not as high performant as CUDA or HIP code if you program in OpenCL, and it's more cumbersome to use because it's a more low-level language. So in principle, you can write portable code though. And then there's SYCL. So SYCL is is newer. It's been around for some time as well. I'll talk a little bit more about that. But that's a single source, high-level standard C++ programming model. And it can target a range of heterogeneous platforms. So in principle, it can work with any device that is supported by the compiler and the runtime. If there's a backend implemented for that, and so you can target CPUs, GPUs, FPGAs, all with the same source code, which is quite nice. And if I say GPUs, I mean GPUs from all vendors. And then on the right, we have, so these are basically explicit programming languages. And then we have here pragma-based approaches where you add pragmas to your source code, openACC with accelerator directives for Nvidia and AMD that works with C, C++, and Fortran. And openMP that's been used more and more. I've been looking into this a little bit for our Cosmos system. So this is becoming more mature than it used to be. So it's actually also something useful to look into if you have source code that's Fortran C or C++. And then there are high-level abstraction layers for C++, like Cocos, developed by DOE labs for portability, that basically abstract these lower-level languages via a library that they're developing, basically, and Raja and Oka. So they also can use multiple backends, including CUDA, HIP, and SYCL. And with that, in principle, if you use Cocos, you can also program or write software that then, in principle, runs on all the different computers. So if you go back here, you have these are AMD APUs, Intel GPUs, and you'd have like Nvidia GPUs on our systems. Yeah, and so what is SYCL? So SYCL is a C++ programming language for heterogeneous parallel computing. It's developed by the Kronos Group. It's an open specification. They also develop OpenCL, SPIR-V, Vulkan, OpenGL. You've heard about those. And it's based on standard C++, and it has extensions for parallelism. So there are new classes, functions, and programming constructs. And they provide APIs and abstractions, for instance, to find devices like CPUs, GPUs, and FPGAs to execute the code. And thing is, it's all C++, so there are no pragmas. It does borrow some concepts from OpenCL, like a platform, a device, work group, and range. So the language is a little bit different from CUDA and HIP, but it all maps basically to similar concepts. Like I said before, you have a single source code. It's a single source C++. It supports implicit or explicit data transfers. When I say data transfers, I mean transferring data between, so if you use to CUDA or HIP, host and device memory, so between the different devices that you're working with. And the portability is basically achieved by targeting different backends, right? So it's not tied to proprietary solutions, so it provides this layer above, and so it can work with OpenCL. So you don't have to write OpenCL code, but you can write SYCL code, and then it uses an OpenCL backend to run on Intel, AMD, or Nvidia GPUs or FPGAs, or the specific graphics backends for AMD, Nvidia, and Intel GPUs, level 0, CUDA, and ROCm, or it can target OpenMP, so you can run in principle code that you write also on any CPU, right? So with multiple threads. And yeah, so we can target a range of heterogeneous platforms. It's based on this specification by the Kronos Group. The first one, I believe, came out in 2000. Well, must have been before 2014 because here it says SYCL 1.2. But there have been different specifications coming out, and the latest one is called SYCL 2000. Was ratified in February 2021, and the first full compiler implementations that support this fully as with the Intel oneAPI compilers was about a year ago or something like that. And how it works, you have your C++ source code and the C++ device code. And then you have the compiler that creates the object files, right? And a SYCL device compiler that generates a device intermediate representation, the linker that links things together, and then you have a binary plus device intermediate representation where when you execute it, the CPU portion runs on the CPU, and then device code executes on the GPU. And so this is a little bit outdated, but I thought it's still useful to have that slide on there to look at the SYCL ecosystem. There's a little bit more to it, but while ago, a few years ago, this is probably from, I don't know, a few years ago, there's basically three main projects that were writing compilers for SYCL or support for SYCL standard. So Intel's DPC++ compiler, so that's basically what is called oneAPI now. And Compute CPP from CodePlay. So CodePlay was actually acquired by Intel, and this is a division in Intel. They're still independent, sort of, but they basically now work with Intel on the compiler. It's an open source LLVM-based compiler, and also the backends to target Nvidia and AMD backends. And then there's a compiler infrastructure from the University of Heidelberg that was called HipSYCL. It's now called Adaptive CPP. And yeah, like you can see, so basically you can target a CPU or you can target OpenCL, and that happens automatically. So you just have to tell the source code which backend you want to use. And then, either you target level 0, you can run on Intel GPUs with a level 0 backend, or with a CUDA backend, you run on Nvidia GPUs, and then with a ROCm backend on AMD GPUs. And so that's in principle how it works. The same, of course, for the other compilers. Yeah, so these are the main implementations that exist at the moment. There are some experimental ones as well, but Intel oneAPI is basically an open source compiler and software infrastructure with also libraries by Intel. There's been a little bit like lots of name changes and renaming over the last few years, but it's becoming stable and clear what means what. I'll briefly mention also UXL on the next one or two slides. And it supports SYCL 2020 for Intel CPUs and GPUs. It supports, of course, also CPUs via LLVM. And so it's an LLVM-based compiler infrastructure. And it supports NVIDIA GPUs and AMD GPUs with the CodePlay oneAPI plugins that then target basically CUDA and ROCm. And Adaptive CPP is more community-driven, as this is something that you like. And it also supports, it's also LLVM-based. It supports LLVM-supported CPUs and Intel, AMD, and NVIDIA GPUs. And then there is Celerity, which has SYCL abstractions for distributed systems. I cannot tell much about this because I'm not familiar. But just for you to know that this is out there. And then I want to mention oneAPI. That's the and the Unified Acceleration UXL Foundation, which was founded about 1.5 years ago, something like that. And so this started as an Intel initiative for a unified programming model, and it's now evolving as an open standard under the UXL Foundation. And the idea is to have a heterogeneous cross-vendor programming model that contains both SYCL, so the whole thing is powered by SYCL underneath, and but also have libraries that then can be used to abstract away the call of individual libraries or of specific vendors. So you have something like oneMath, and it's initially underlying math kernel library, so you have math functions. And if you use the oneMath API and you're running on level 0, you're going to get Intel's MKL for Intel's GPUs for your math operations. If you run, say a fast Fourier transform or a matrix multiplication or some solvers. And if you're running on an NVIDIA GPU, you'd have something like QBLAS, for instance, for matrix multiplications, or QFFT for fast Fourier transforms, and interfaces via oneMath, so you don't have to change the source code. if you want to use one or the other. So that's the basic idea. And yeah, so you can see this. So you have this, oneAPI with the different libraries. You have your open source projects here, these open libraries, and you can build those from open source. You can also actually go to the website. This is all freely available, and then you can target any of these architectures basically when you're running your code. Intel CPUs, RISC-V GPUs, and so on, CPUs, and then ARM CPUs, x86, and then AMD, Nvidia, and Intel GPUs, of course. So if you look at the timeline, OpenCL, it's a little bit younger than CUDA. So CUDA, that's why CUDA is dominating the market. Nvidia has been developing CUDA for a long time, and they've been putting a lot of effort into having a very, very robust ecosystem and a very performant software and hardware infrastructure. Lots of support for developers as well. And then SYCL was basically started in 2014. Yeah. Okay, so that was the first release then, official. And that's where we are now. And so AMD started later. So about 2016, they started to make publicly available their open source ROCm infrastructure. And so, yeah, that's basically how the ecosystem looks now. And the idea is, hopefully if we have something like oneAPI, we could in principle write code once and don't have to worry about using, vendor-specific programming models. Now, resources. If you are interested in resources for learning about SYCL, this book here is actually free. You go to this link. It's actually a pretty nice book. It doesn't hurt to look into this. If you learn SYCL, you also learn something about CUDA and basically data parallel computing, and if that's of interest to you. And these are the two major SYCL implementations at the moment. Or you just go to this website, the Kronos Group, kronos.org/SYCL. It has a lot of information, SYCL specifications, reference, documentation, and tutorials. And then here, SYCL Academy, that's literally very nice tutorials. You can go through this at your own pace. There's slides and source code, and so you can actually learn step by step. This is a great resource actually. There's also SYCL reference inspired by cppreference.com, and it has short description of the entire SYCL 2020 API. And of course, the specifications remain the canonical reference document. Now, if you're familiar with CUDA, I'm familiar with CUDA, so that's why I put this slide on. Actually, I grabbed it from somebody else, but it's basically something that I wanted to put on slides as well. And I forgot to put the credits here. Apologies for that. But you have a block of threads. So when you parallelize your code, you have many threads running, and a grid of blocks, right? And that maps to the GPU. And in SYCL, it's very similar. So you have a work group that corresponds to a block, and a work item that is basically a thread. And then something that's called an ND range. So a range basically of number of threads that you're running, and then this ND range can have multiple dimensions similar to CUDA grids. And so ND range basically is the grid of threads that you're launching on a given device. And instead of kernel, SYCL language talks of command group. That basically means commands that are issued in a group that belong together. And then we have a queue. So something gets queued into a queue. A command group basically gets queued for execution into a queue. And that corresponds to CUDA stream, right? So you can have different queues similar to CUDA streams where you have in principle. So that allows you to do something like task parallelism. Now this becomes a little bit confusing because there's something called local memory in CUDA, which is different from what SYCL mentions as local memory. So local memory is basically the memory that's local to the processor. So it's basically the user managed cache memory. So that's called shared memory in CUDA because it's shared between different threads in a block. And here it's called local memory because it's local to the work items in a work group. Yeah, and then there's unified memory, and it's unified shared memory USM in SYCL, and we have graphs and SYCL flow in is the equivalent. So SYCL basically builds a graph of your code and then launches the command groups in a queue according to the directed acyclic graph of your software that you have written, such that you have correct execution of your source code. Now, if you have a CUDA code and you want to port your code to SYCL, then you can use this using a tool called Cyclomatic migration tool, where you have a CUDA source code and you use this compatibility tool, this Cyclomatic, and you translate your code. It's usually, depending on how complex your source code is, it gets you 90 to 95% there. A human readable source code, SYCL code with inline comments. So the inline comments help you basically if there are issues with the translation or something you need to be careful with and pay attention to. And then, so what you have to do after that is to complete your code and tune to the desired performance. And then you'd have a SYCL program starting from a CUDA program. Now, it's not that simple. If you have a very complicated or large software base, it can take some time, but more about that later. So let's talk a little bit about, I don't know how well you can see this. This is, sorry, it's a little bit small, but just, if you translate a CUDA code to a SYCL code, you'd see you'd have basically equivalence. You can see how from the structure it looks very similar. You have the header file here. You include the CUDA header, and in this case, you just include the SYCL headers. Then you can define kernels. For instance, here, if you have a vector addition, so that's a CUDA kernel, vector add kernel. You have the same thing. It just is a kernel function in this case. You can have device memory allocation, so CUDA malloc, where you allocate memory on your GPU. You can allocate memory on your device as well. So you have a SYCL malloc device function in this case. So that's the equivalent. You can copy host to device, so use the CUDA memcopy functions. And here you have basically the queue that you have set up. So the queue has been set up here. So you have a SYCL queue, CT1. That's this one here, and there's the memory copy operation. So you're copying basically that data. It looks pretty similar. You can have wait functions to have barriers if you need that. And then you submit your kernel task. And so in CUDA here on the left, you launch that kernel with a certain number of blocks and threads. And what you do here is you have a parallel for, which is basically a for loop that executes the kernel in parallel. So you have the vector add kernel that is up there. It gets added to the command queue, and then you have this ND range here, and with a certain number of blocks and threads. So if you want to call it blocks and threads, for instance, and you can have like different dimensions depending on the problem that you're launching it to. So it looks a little bit more verbose, but once you get used to it, becomes actually pretty straightforward to use. So how do you determine where the code executes, right? So you have the single source code, and then you have the portions, the regular CPU code, but you also have the device kernels, right? And so you're submitting the kernel to one of the queues that you have defined, and then it runs basically on those devices. Now, you use a device to dispatch work or to allocate memory. So we've seen this on a slide before already. So, there's a memory allocation in a certain queue. And then there was the execution of the kernel in the same queue. And it's out of order by default, but it can be created in order. So if that's important and you know that, kernels have to follow a certain order. And the queue submissions are asynchronous. So that's similar to CUDA. You basically execute the queue and then you can continue with the source code that's not launched in a queue. And here's a simple example on the right, which, just this is the device code and everything else is host code, right? And the important pieces that we see here again, so we include SYCL, HPP, our header files, and we create a queue. In this case, it's an implementation chosen default queue. So if we don't tell actually where to run, then there's a default queue that's being picked. If you only have a CPU in your system, it's going to run on the CPU. This is something different. So this is not allocating the memory explicitly. So there's two different ways of handling memory, and I'll explain this a little bit in a few slides. But that's basically creating a buffer for the data, and that's host allocated on the host. And then we would submit to the queue using this handler source code here. And here we have this parallel for, so the parallel construct that's executing on the device. We have something here before that's called an accessor. So that's an accessor. So I'll get back to that, but that basically is the second way to handle memory. Instead of using unified shared memory, USM, you can use these buffers and accessors that handle the memory automatically for you. And yeah, so you do this parallel for loop. And the ND range is just a range here of size. So in the size we defined it 16. So you'd have basically parallel over 16 elements, and then you let the SYCL decide in this case automatically how to split this up in terms of like work groups and work items. And that's the device code. So it basically just assigns to A and so we've used this accessor here so we can access the data of B as A, right? So B is sitting, remember B is sitting on there's a buffer that's sitting on the CPU side. And now here we have an accessor created in that queue, and that queue is running wherever it's running. It's running a default device, right? I mean, it could be a CPU, it could be a GPU. This accessor that's named A into B. And so behind the scene, the memory copies will happen automatically. And yeah, so this is the device code that's being executed basically. And we have this variable IDX generated automatically for each work item or thread that's running in a work group, right? So each thread would basically assign a different value to A. And yeah, and then we need to get access to that buffer again on the host. In this case, it's called host accessor. We want to have A. Yeah, basically the data that we've filled in here. And then we can print the results. So that's a very simple SYCL code.
Andy,
Yeah.
we have a question from Carl
Okay.
about the CUDA to SYCL vector addition conversion. Is it a cyclomatic output? I think it's maybe two slides back.
No, this is not going to be a cyclomatic output. If you get a cyclomatic output, you will get comments in the source code as well. I haven't tried it. I mean, you can just try and see what you get and how good. I mean, this is always nice. I mean, this is always what I recommend if you want to see how something works or if how well it works. You take some relatively simple examples of something that you think might look different from or might be challenging for a compiler or for a tool that you're using, and just run it through it and see what it gets you. But this is not. So this is taken from an Intel slide deck that I had from somewhere, so I don't remember if this was. I doubt that this is a direct output for sure, if you get the output from Cyclomatic, you'll have comments in the source code as well.
Carl also wants to know, can SYCL make recommendations or rather automatically determine when and whether to offload to GPU?
Well, that would be nice, but that's up to the user. So you have to have an idea about which are the computational bottlenecks in your code and what should be offloaded. You know, which parts of a code are data parallel. And then, I mean, you still have to optimize your code in certain ways, right? I mean, if you don't have core-less memory, it's similar to CUDA if you don't have core-less memory accesses and so on. Because under the hood, the compiler still needs to generate code that then maps to the architecture. And there's many similar optimizations to CUDA code that you may have to do. And so in that sense, the portability and so portable is always going to be portable. Performance portability, that's a different issue. So to be honest, I mean, you cannot expect the code to run perfectly, say, via openMP backends on a CPU and be as performant as it might be, and at the same time, say, on an Intel GPU or an Nvidia GPU. But you get code that runs in parallel, and it runs reasonably well, and so it may just be good enough, right? If you don't always need the last few percent of performance.
Okay, thank you. No more questions.
Okay. Yeah, so that was basically this very simple SYCL kernel, and then yeah, device discovery, right? So you can do things like you know, you looping basically. So what are we doing here? You can list available platforms and devices. So platform is basically the collection of devices that share the same backend. And here's the source code on the left where you know, we have a get platforms function, and then we can say for yeah, so what are we doing? Yeah, we're looping over all the platforms. We're printing, you know, which platform we have, which backend basically, and then we're looping through all the available devices on that platform, right? And then we're using the get devices function, and we're printing, you know, all the different devices. And that's a sample output of one of the development workstations that I have for testing the code that we're developing on Intel Arc graphics GPU basically. That's a Battlemage B580 GPU. And you can see, so there's a Intel oneAPI unified runtime over level 0. And so that with that you can use the Arc B580 graphics card. It also found OpenCL backend, and you can use the OpenCL backend to run on the CPU. In this case, it's an Intel Core Ultra 9 CPU, or you can also run via OpenCL on the graphics card. And so you have these functions available for device discovery, and then we've seen this before. You know, you can have these different queues, and you can bind them to a single device. And then the work that's submitted to the queue executes on that device. So you can have a queue and run on GPU 1 in your system. If you have a different GPU, you can run on GPU 2. If you have a FPGA in your system, you run on FPGA on your CPU. So I was on a SYCL tutorial a while ago, and it's very funny. There was a instructor from AMD, and he was all excited because he had this workstation where he actually had different vendors GPUs in their FPGA CPU, and he wrote this few lines of code, and this line execute, you know, basically this portion executes on the FPGA, this one on the CPU, and this one on the GPU. It's actually quite neat to see. Or you can have multiple queues also bound to a single device, and then they execute on the same GPU, for instance. And yeah, memory-wise, you know, it looks pretty much similar to, yeah, you have shared CPU and GPU system. CPU, of course, has its CPU memory, and then typically there's a PCI Express bus that connects GPU memory and the GPU to the CPU, and so that's similar to CUDA. And I just want to mention that there are these two ways of managing memory. The buffer accessor model and the unified shared memory model. So you've seen both a little bit before, and there's different ways that USM can be allocated on the host, on the device, or shared. And so if you do this device allocation, obviously you can use the memory only on the device. Host allocations is normally allocated on the host. Well, of course, if you want to use it then on the device, you have to transfer it manually. But you can access it from the device in that sense. Shared it migrates as required, and so you don't have to that's easier to handle in some sense. But of course, this can have performance penalties. And the way this works is, we have this malloc device function, for instance, to allocate memory on the device. And then you'd have your queue, for like the queue in which you are launching your kernels, also your command groups. You can have memory copy operations where, you've seen this already, right? Where we transfer data from a CPU to the pointer on the GPU. So explicitly getting the pointers to the memory locations, right? So that's not hidden from you. And when you're done, you copy the data back to the CPU. So that's the same as, you'd be doing this in a CUDA code or a HIP code. And when you're done, you can free the memory again. So you can have this explicit memory allocation. Here is the shared memory. So you can, have this shared memory that's basically the unified memory in CUDA language. And then you can just use this on the host as well as on the device. And then you can free the memory. But, with this, it's nice and easier to program, but you have to be careful because the memory copies, of course, still happen behind the scenes. So if you don't know what you're doing, you may have poor performance depending on the platform that you're using. And finally, there's buffers and accessors. So this is literally what I've been mentioning before. And so the SYCL buffer manages data across the host and any number of devices. So the accessor is then used to request access to data on the host or on a device for a specific SYCL kernel function, right? So you have something where you have a buffer and it gets allocated in host memory. And the buffers and the accessors take care of memory migration and dependency analysis. And so if you look at the source code here, this is exactly the same source code. So we're creating this buffer B with some data. We've defined this here as an array, and we're sticking it into this buffer. Okay, so now we can handle it with these buffers and accessors. And in this queue, where we are executing on a certain device, and we could have selected the device in this case for this simple example is just the default queue, but we could have selected, say, the level 0 backend and then run on a GPU, an Intel GPU, for instance. Now we can say, okay, we want to access that buffer, okay? And so now we have created an accessor that's actually inside of a command group that's running on the device. So what's going to happen is actually that, source code compiler analyzes the source code, builds a graph of dependencies and knows, okay, well, this needs to be in device memory at that time, and it will copy to device automatically, allocate the memory and copy that for you, the data to device memory. And then you can basically access the data on the device. And the same when you come back, you say, okay, well, now I need access on the host again. So host accessor function. And what happens is then that the data will be automatically copied back at this point. And finally, the last few things I want to mention is just the execution model. It's in principle similar to what we know from CUDA or HIP. So we have these work items and the ND range that I was talking about. So work item is basically like a single thread. It's a it's a kernel function that's so work items execute these kernel functions. You can think of it as a thread of execution, right? And it will execute a SYCL kernel function from start to end, right? So here, there's not much in there, but I could have, of course, a longer kernel with multiple operations instead of just this assignment operation. And it can run on CPU threads, SIMD lanes on a CPU, GPU threads, or any other kind of processing element, right? And then we define an ND range in which we define, so these kernel functions are invoked within an ND range. And as you see the ND range here, and you can see that the work items, they're basically grouped into work groups. So I have work groups, and I have multiple of those, right? So I can define an ND range. In this case, I would have a work group size of 4, but I have an ND range of 4 by 4, so 16 times 2, right? So I would be launching basically 32 threads if you want so, and they are grouped into work groups of 4 threads. And earlier we've seen basically a simplified execution model that has been using just the SYCL range and not the ND range, where you just specify the total number of threads and then let the runtime basically handle that automatically for you. That's usually not ideal, and so typically you can do this for simple problems, but typically you will want to define the ND range yourself. And in terms of the memory model, that's also kind of like similar to CUDA. So you have private memory for the work items, and of course, that the local register memory, basically, that's very fast, but you don't have as much. And then you have local memory that you can use. That is basically the shared memory in CUDA. And the global constant memory. So the local memory is like accessible by all work items in a work group. That's similar, like to all the threads in a block in CUDA language. And then you have the ND range where basically all your running threads that can all access the global and the constant memory. And so I hope this was a useful overview and introduction to SYCL. And what I want to do now is, because we don't have a lot of time, is just to actually tell you, well, if you have a very complex code, can you actually convert this into SYCL or write this? In this case, it is a porting effort of Amber. And I will briefly talk about Amber. I'll probably skip a few slides because I have quite a few slides. But we don't have enough time. But so one thing that I wanted to say is, and this holds for other fields too, but also biomolecular modeling, and I like this graphic particularly by Tamar Schlick from this publication in 2021 that basically demonstrates how the simulations and scientific simulations and related discoveries that come from simulation have been going hand in hand, usually with development in computer technologies, right? And in particular here, since the mid 2000s or 2010, really it's been taking off a lot. We had GPUs, for instance, and now there is a lot of course, developments along AI and machine learning that is happening. And so with that, we started with Amber development in the about 2008, 2009 to develop code for GPUs, and it's been going on for some time. And the last few years, I've been looking in a collaboration with Intel to get that to work also on Intel GPUs. And so Amber is a molecular simulation package that has both the functional form that defines the interactions between the biomolecules like proteins, lipids, and so on. And it has the molecular dynamic simulation package, which has been around for, well, I guess now it's over 40 years. The one code that's in there that is a high-performance molecular dynamics program. And that is used for biomolecular simulations. to study things like proteins, building blocks of cells and tissue, and basically understand how life works at the nanoscale, right? And it's used also in computational drug design. There's the website in case anybody's interested in that. It's pretty widely used. So we have, the users counted through licenses, and Amber Tools is the free portion that has a lot of preparation and analysis programs, and also a less high performant but more molecular dynamics code with more functionality. And so some of the papers that I was involved in, you can see it has like thousands of citations and gets like, several hundreds of citations per year. So it's actually nice to see that people use these the software for real science. And yeah, you can see over the years, this is outdated. I don't know how it looks like, but I assume, it's been continuing on a certain growth. And nowadays you could put some, say, AI on it as well, and you'll see that taking off probably. But yeah, molecular dynamics is pretty widely used in biomolecular modeling, and the same for different software packages. So there are different software packages which can do similar things, and so Amber is one of them. It's pretty widely used, and I think so part of that has to do with its high performance on GPUs, similar to also GROMACS, for instance. And what we do is we model these molecular interactions not with quantum mechanics, because this is very expensive computationally, but instead we use, in Amber at least, what I'm going to talk about now, these simplistic force fields. So the equation looks more complicated, but of course here the complicated part is all hidden in this Hamiltonian here, or how these energy functionals look like. So it's a relatively simple ball and stick model, but you have to compute also these pieces here, where these are charges that are sitting on these atoms, and it's basically the charge-charge interactions between all atoms, and then some other non-bonded interactions that we compute. And yeah, so this quantum QM is expensive, more accurate in principle. Force fields less accurate in principle, but super fast. And so this is what we can do when we do something like this, where we have hundreds of thousands of atoms, and we can actually study the dynamics. For instance, that's from a project where I studied in the past cytochrome C oxidase, and how water molecules that are produced in the reaction center here, and that happens. So this is an enzyme that everybody has in their cells. And so this is the last electron acceptor, where oxygen comes in and gets reduced to water. So the oxygen that you're breathing, and the water has to go out somewhere. And so we studied this here. And about molecular dynamics, one thing you have to know is the relevant timescales. So in terms of biology, we're interested in, things that happen somewhere here on the, nano, micro, millisecond timescale. The problem is, for the simulations, the time steps that we take are on the order of femtoseconds, and we cannot make them longer because otherwise the numerical integration algorithms are not stable. And so we need hundreds of millions of time steps. And if you want to finish the simulation in a reasonable amount of time, that means less than a millisecond wall clock per time step to compute all these interactions between hundreds of thousands of particles. So it needs to be fast. And these are all timings, but you can see that, this is about 400,000 atom system. This is the computational throughput that we get in 24 hours, so in a day. So we wait a day, and how much time in the life of this molecule can we simulate? And so how many nanoseconds, right? So we are somewhere here in the nanosecond, 10 to the minus 9 seconds of the life of the molecule. Back then, on a state-of-the-art CPU node, about 2 with the software implementation that we had. And you can see that on a single GPU, in this case, either consumer hardware or data center hardware, we significantly faster. That's we managed to implement collaboration with many people, very, very high performant code, and with all sorts of tricks where we've been using mixed precision implementation. And so what we're currently doing is we computing most of what we're doing in FP30, so single precision, that's 32-bit floating point numbers, and then do accumulation in actually fixed precision and some pieces in double precision. And if you don't do this correctly, then your simulation basically blows up. So this is the energy in a so-called NVE ensemble, and you're solving Newton's equations of motion, so the energy needs to be constant, and it does that, right, along the simulation. But if our simulation is not accurate enough because we're dialing down the precision, then the simulation actually blows up. So we cannot simply use, for instance, in modern GPUs you can do FP16 operations. You can't just do this, right? You have to be very careful with precision. And so the motivation actually to look at SYCL was basically to enable AMBER to run on Intel GPUs. And of course, SYCL is an open standard, which is nice. And like I talked about, in principle, there's portability across different vendors. Although, I've not investigated this for AMBER. We didn't have time yet for that. But I'm going to show some data, and you can see, so the GPU Max 1550, those are the GPUs that are in this Aurora supercomputer at Argonne National Lab. There are also some and some P3 at the Texas Advanced Computing Center. It's a pretty powerful GPU, as you can see. You can't buy these anymore, so Intel stopped producing these, and so it's not clear what they have up in the roadmap in the future. We'll see what happens, but compared to an H100, at least based on the raw performance data, it looks pretty good, pretty comparable. But also the consumer hardware, if you go to a store now and you buy a B580 for $250 MSRP, compare it to a Nvidia GPU, you get actually a GPU that has a higher FP64 floating point performance and more RAM. So it's actually pretty nice on paper architecture that looks not bad. And yeah, so this is just, I'll skip over some of these. This looks how the GPU is made up of different tiles and stacks and then slices, and then each slice contains basically several of these cores. A core basically is what Nvidia would call a streaming multiprocessor, I would say. And each of these cores then contains vector and matrix ALUs, and for SIMD operations and matrix engines. And yeah, so in putting this all together, that's where you get all this performance from. What was the challenge? So the challenge is, we have a highly optimized kernels for particle force calculations, time stepping, temperature, pressure control, enhanced sampling algorithms. There's many of them for many different code paths, and so there's a lot of source code basically that needed to be ported. In addition, we had these multiple precision models. So there's the SPFP and then a double precision, fixed precision. We have MPI implementation. Some of the code is written in CUDA intrinsics with PTX inline assembly code. So if you run Cyclomatic, it's not going to know what to do with any of this, of course, right? And CUDA code history also had many years of initial development until there was a first stable version of the code. It's not there's so many kernels and so much functionality. It's not like a few months of effort. There's multiple years of effort, and overall over a decade of contributions from dozens of developers. So not easy to rewrite from scratch. Just some statistics about how many header files, source code files, and non-spaced lines. So it's a pretty big code, but this is exactly what I've shown you before. And so that's actually how we started. And when I say we, I'm talking about my collaborator at Intel who did all the heavy lifting, Guochen Chen. And we started with AMBER 20, and in the meantime, when after AMBER 24 came out, so we had a partial code port that was working, and then we actually abandoned that and restarted with AMBER 24 because there were too many changes. And we thought by that time we understood what we've been doing, but it's easier to start from scratch than to integrate the changes that, into the code that we had developed so far. And now we're done with AMBER 24. It's feature complete and will be released soon. I hope, at least. I have so many things on my plate to do that I hope I won't delay this any longer. There's a comparison here. If you look at, okay, well, you have a kernel on the left, or 2 kernels on the left, and then they got translated into kernels on the right. And this goes back to some questions. The question earlier, was this generated by the cyclomatic? So actually, this used to be called DPC++ compatibility tool, but you can see here, right? I mean, there's a comment inserted, DPCT, and then some numbers for certain issues that it finds and comments that it makes, right? And it gives you some information what you may have to be careful for or check if performance is not as expected, for instance, in this case. And yeah, so we ported the code. It's actually done, and there are always small energy drifts. So because we have lots of atoms on the scale that I showed it earlier to you, you can't see it. So this is a scale where you see these small energy drifts. So at each time steps, the MD simulation fluctuates around an average energy, where the kinetic energy goes into potential energy and vice versa. And you can see that effectively the SYCL code executed on an Intel GPU matches the CUDA code executed on an Nvidia GPU very well. In terms of benchmarks and performance optimization, I have slides on performance optimization, and I'll just skip over those because I don't have time, but I have them in the slides if anybody wants to look at them. I presented this before at an iWorker conference, so this is all public in any event. It's basically guided by Intel OneProf for profiling, and OneTrace for tracing, and then VTune for optimizations. Yeah, so there's a bunch of key optimizations that we did for some of the kernels, and I'll just go over those issues that we found, and then we managed to improve, like you can see here some of the non-bonded forces, and then after the execution, the kernel time significantly went down by over a factor of 2. So sometimes you have to really dig into and see what's happening. And you can see the performance evolution for running this benchmark system. That's a 1 million atom system example on an Nvidia H100 with a CUDA code, or an A100 with a CUDA code. And this is running on one tile that's basically half of a GPU Max 1550, starting out at 20% of the performance and then doing different optimizations, profiling the code, optimizing it, and ending at over 50% using half of the GPU. That's pretty good. Getting more than half of the H100 performance on half of the GPU. Now, when you're scaling to 2 tiles, so remember I talked about these tiles and stacks and so on. So the GPU Max 1550 is basically 2 tiles that are exposed as 2 different devices, and so you have to program them explicitly because you can use 2 tiles with implicit scaling and let the device just handle it and the runtime, but that's not very efficient. And so the best that we got with explicit scaling was using both tiles 40% of an H100, and so that's actually worse than just running on a single tile. So that, there's basically communication overheads and stalls that are happening, and then we use MPI and to handle the communication between, so splitting up the work onto the 2 tiles, as treating it as 2 different devices, and then using MPI under the hood, and with that, we got a performance of 82% of an H100, which is actually pretty good, I would say. And these are all the benchmarks that we have in Amber, and I won't talk much about it, but here's a smaller benchmark, and here's a larger benchmark for one type of simulations, and there's a different type of simulations again for smaller to larger benchmarks. And so there are performance differentials. So this is the relative performance. Green is an Nvidia H100, and then we have different Intel GPUs here, either running on the entire GPU, only one tile, another data center GPU, or the consumer GPU. And you can see that consumer GPU is actually pretty good for that cheap price that you have. If the workload is smaller, then there's kernel launch latencies that are not as efficient on the Intel level 0 with SYCL than with the Nvidia CUDA. And so we're getting a bigger hit. So we may be only 50% of the performance versus the 82 that we got for the STMV. So those are some of the things to keep in mind. And if you have longer running kernels, like in this example, that's a different type of simulation we can do with Amber. Also molecular dynamics, but there we can actually get almost the same performance. So it depends a little bit on the workload, the size of your kernels, and how sensitive you are to kernel launch latencies. And that's just a different representation that shows the different GPUs, the performance relative to the H100. Yeah, so that SYCL code actually performs quite well on the GPU Max GPU compared to the H100s. For the small workloads, the Intel GPUs suffer a little bit from driver side inefficiency, so these kernel launch latencies. That's just something that's there. There's not much that we can do in terms of like programmers, software engineers, application developers. The Intel Battlemage B580 performs really well considering its very cheap price. And there is, of course, still room for performance improvement for some of the major kernels. But that's, at the moment, we don't have the resources to look at this. And with this, I'm at the end. GPUs are everywhere. SYCL offers a portable way to develop vendor-agnostic C++ code for heterogeneous systems, including GPUs. So I hope this became clear. I hope I introduced you a little bit on how SYCL works and how you can use SYCL to program C++ for arbitrary devices. And then, Amber is widely used MD software package for biomolecular simulations, and we've used Intel oneAPI to port it to the high-performance MD engine of Amber from CUDA to SYCL, do some optimizations of the SYCL code, and it's now numerically stable and shows strong performance on Intel data center GPU Max hardware, but also the the consumer hardware. And with that, I would like to thank Guochuan Chen at Intel, and he has been doing much of this porting work of Amber, and he had support from many Intel software engineers as well. Ram Ramanujan and Christoph Duncan are managers in Guochuan's group. Kitur was running the Intel oneAPI Center of Excellence programs, was my contact that was unfortunately shut down this program with all the restructuring that Intel is going through. But there was some funding for doing this from Intel, and then also National Science Foundation with its different grants that support our research and the supercomputers that we have at SDSC. And with that, thank you for your attention, and I'd be happy to stick around for some questions if you have some.